Good afternoon, everyone. We're just delighted to see you here and to see so many of you here. I'm Ann Curzan, Dean of the College of Literature, Science, and the Arts, and I'm here to introduce Bing Zhou, the Donald A. Glaser Collegiate Professor of Physics. While we wish, and I know we all wish, that we could hear from and celebrate with Professor Zhou in person, today's lecture is being streamed live to maintain social distancing. And if you would like to, please feel free to click on the CC button at the bottom. This will allow you to show subtitles or live transcript as we go. And I will say one of the benefits of doing these as a live stream is that so many of you can attend. And again, we're delighted. You will be able to ask questions throughout, and I'll remind you of this at the end, but there's a Q&A button at the bottom, and you're welcome to submit questions during the lecture or at the end, and I will moderate those questions after the talk. So collegiate professorships are named at the discretion of their recipients to honor an esteemed faculty member, colleague, or peer. Professor Zhou chose Professor Donald A. Glaser as namesake of this professorship, paying tribute to his significant contributions to high energy physics. In 1949, Donald Glaser completed his doctoral coursework in physics at the California Institute of Technology, after which he joined the U of M faculty, where he earned the Henry Russell Award in 1953 for his commitment to teaching and his early promise in research. His focus was elementary particle physics, and his experiments required the use of cloud chambers. His interest in improving their visibility and efficiency led him to the University of California, Berkeley, to work with Nobel laureate Luis Alvarez. That collaboration contributed to Dr. Glaser inventing the bubble chamber, for which he received the Nobel Prize for Physics in 1960. He was just 34 years old, one of the youngest Nobel Prize winners ever. His career at Berkeley branched into molecular biology, and he co-founded the CETUS Corporation, which developed cancer therapies, interleukin-2 and interferon. He died in 2013 at the age of 86. Professor Bing Zhou has also contributed significantly to her field, particularly through her study of electroweak physics with boson productions, which is the major channel for Higgs discovery. She is also known for developing the Large Precision Muon Spectrometer and for her extensive body of work related to ATLAS, the particle physics experiment at the Large Hadron Collider. Her expertise related to ATLAS is well documented, going back to 1992, and aided in the discovery of the Higgs boson. Bing Zhou received her PhD in physics from the Massachusetts Institute of Technology in 1987. She conducted her postdoctoral work at Boston University, where she began teaching in 1991. In 1998, she came to the University of Michigan as an associate professor of physics, rising through the ranks to professor in 2002. She was first named the Donald A. Glaser Professor of Physics in 2013 and renewed in 2018, and we're delighted now to be able to do the lecture. Since 1999, Professor Zhou has been principal investigator of the U.S. Department of Energy ATLAS project at U of M, administering grants totaling more than $1.5 million a year. These funds support the work of many U of M students, researchers, and faculty, some of whom are residents at CERN, the European Organization for Nuclear Research. In the last decade, her research has directly contributed to more than 75 papers related to the ATLAS experiment at the Large Hadron Collider. Her research has garnered her numerous honors. In 1994, she received a National Science Foundation Career Development Award for scientists, and in 2001, she was elected a Fellow of the American Physical Society for her, and here I quote, outstanding contributions and leadership in the development, construction, and exploitation of complex detectors in fundamental particle physics experiments. She was a CERN Science Fellow from 2004 to 2005, and she is a sought-after reviewer of articles for leading physics journals such as Physical Review Letters and Nuclear Instruments and Methods. Her commitment to her research is complemented by her dedication to teaching. She is highly regarded by her students whose evaluations describe both her teaching and her courses as excellent. She teaches across an impressive range of levels, from general introductory courses like Physics 140 to the most challenging, geared toward graduate and PhD students, such as classical electrodynamics and particle physics. At the University of Michigan, Professor Zhou has served on the executive committees of the physics department, Rackham Graduate School, and the Atlas Collaboration. In 2010, she undertook the Herculean task of organizing the first year of LHC Physics International Conference, which was held at the University of Michigan. We at the College of Literature, Science, and the Arts agree that Professor Bing Zhou's many contributions to physics, her department, her students, colleagues, and this university make it most fitting she be named the Donald A. Glaser Collegiate Professor of Physics. Please join me virtually in congratulating Professor Zhou on her many achievements. And here I'm gonna clap and just know that you have over 130 people clapping for you right now. And we are just delighted that so many people can be here to celebrate your career. So before I turn the floor over, and I always, I love that we're now doing this at the beginning, I'm gonna ask you a couple of questions. And the first one is, how did you get into your field?
Actually, I get into this field is something like by chance. So in I think it's 1978 Chinese New Year period, I suddenly surprisingly received a admission letter from University for Science and Technology. So they asked me to study nuclear and particle physics. I was surprised because I didn't choose to study in this field, but I had no choice. So I went to university, USTC, studied particle physics. However, when I learn more and more, and I enjoy very much about in this field. So by chance, again, 1982, Professor Tim from MIT visited University of Science and Technology. And then I was by chance at the university. Then he meet with me actually in 3 days, every day, 2 hours, discuss about the particle physics and so on. And I took his exam, and then he grabbed me to MIT to study particle physics. Then I become his graduate student, and then from that time, I just move on in this field.
And I think it's always just, thank you for sharing that story. And I think it's always just helpful for students to hear how we land where we land in our careers. And so my second question is, if you can share with us what you find to be one of the most rewarding aspects of research in your field, or another way to put this would be, what gets you excited every day to do this work?
I just would like to see everything I work, it works. The simple word is it works. When I was a junior faculty, I made a radiation detector by silicon, and I installed in the L3 experiment. And that was during the lab 2. Then there's one day in the hallway, Professor Becker from MIT, he was the professor I worked very closely in the past, suddenly tell me, hey, it works. And then I say, it works. Then I suddenly recognize he means the detector I built in the beam worked. And I was so excited, I'm very happy to hear that. And then later on, for many research topics, because when you do the research, you're not sure it will always work. Whenever I see it works, I feel so exciting and I feel so rewarded. No matter if I build a detector or do physics analysis and so on. So this is something I feel the most rewarding words, it works.
So you know the feeling, and then you can anticipate what it's going to feel like.
Yeah.
You know that it works.
I also tell my student that if something you did, it works, that means you succeed. Otherwise, it may fail and so on. So anyway, so that is the rewarding. I always continue to see this happening in the research.
Wonderful. Well, with that, I will turn the floor over to you for your talk, Build the World's Most Powerful Microscopes for Discoveries. So I will turn the floor over. I look forward to the talk.
Thank you very much. Can let me share my slides? Okay, so in this title page, I just show you a beautiful picture. First of all is the Large Hadron Collider on the ground of Geneva, 100 meters is a 27 kilometer circular tunnel. Okay, you can see the part of the accelerator. This is only very, if you ride a bicycle, it will take 1 hour to go through the circle. And then this collider actually collided high energy protons. Then we build the huge detector on the ground. Also, as I show you here, is the ATOS detector we build to study particle physics. So that is the major topic I'm going to tell you today. So scientific instrumentation is the key for discoveries. I only would like to give you very few examples here. Here I show you the cells, which are the basic unit of life, was unknown for a long time until the microscope was invented. Then people starting to look at these cells at the micrometer level, 10 to the minus 6 meter. Then a bigger discovery in life science is the DNA, okay, which carries the secret code of the genetic inheritance of life. And only be able to discover it and observe it is when much more powerful electron microscope was invented. Okay, so now you see that it has been a sensitivity better than 25,000 deep. Particle physics is much more ambition. Would like to know the fundamental building blocks of our whole universe, our world. So here, first of all, is the nuclear discovered maybe 130 years ago by the Rutherford scattering experiment, and found out that the atom actually is almost like embody all the materials at the center. So we would like to continue explore the much deeper level. So this is the accelerator invented in 1930. And then together with the big accelerator, that is our super microscope, allow us to find out the deeper structure of quarks inside the nucleus. So the particle physics, that is what I'm working on, the research field, is all about the space, time, energy, and its fundamental building blocks, our universe, and the interaction among these kind of building blocks, and also the law that governing them. So the picture shown below is the four fundamental forces: gravity, okay, which describe the planetary motion in our universe and the universe evolution. And the weak force, this very beautiful, colorful ball is actually the nuclear fusion and governed by the weak force. And the electromagnetic interactions, which we feel familiar with, that hold the atom together. And then is the strong force, which hold the quarks inside the proton and the neutron. Okay, so the ultimate structure of matter and their interactions right now, after many discoveries, are summarized in theory. We call it a standard model of particle physics. Okay, in this model, we have a very simple periodic table, which has the 3 generations of matter And that is in 3 generations of quarks and the 3 generations of leptons showing in the table here. And we also have the vector boson. These vector bosons are the force carrier. In the theory, they were very naturally introduced by the so-called symmetry invariance. So that means if you rotate some kind of symmetry group in the internal structure, and then you have to introduce this vector boson, which actually turns out in the theory that is the interaction force carrier for the metal particles. The puzzle with this theory is this theory requires massless particles. But we know the W and Z, for example, weak force carrier actually is quite heavy. And when the standard model was proposed in the 70s, last century, and many particles actually was not yet discovered. One very special particle, we call it the scalar boson, is a Higgs boson, is trying to address the question about how the W and the Z, these weak boson particles can carry out the mass. That is through a so-called Higgs mechanism to generate the mass. I will give you a little bit more description. So there are 2 critical discoveries in the standard model development. One is in 1974, the discovery of the J psi particle, which actually is the bound state of a charm quark. Okay, so these 2, before this charm quark discovery, many physicists believed that 3 quarks UDS already be able to explain all the observed particles. So physics already understood very well. Only when you discover this new particle, then suddenly it's a new kind of a particle, and then we advanced our understanding of the particle physics. Big step forward. Sam Tin, as I mentioned at the very beginning, was my thesis advisor, and then I will discuss a little bit more about him later on, inspired me in this field for research. Another important crucial discovery is the neutral current, okay, interactions predicted by the standard model and discovered at CERN with the big bubble chamber. This bubble chamber, again, is invented by a Michigan faculty member, actually is Glaser, Professor Glaser. And in this picture, you show that is take this picture from this bubble chamber, and you see the neutrino beam get into the picture. You have nothing. Suddenly, you see the electrons scattered out, and this is the big evidence about the neutral current. And then only after the neutral current was discovered, suddenly it became very urgent to find out the W and the Z boson predicted by the standard model. So I mentioned a few words about the Sam Tin. This is the poster just in front of my office. And then it's related to the University of Michigan. He actually was born in Ann Arbor and was an undergrad student and graduate student at Michigan. So I met with him at the University of Science and Technology in China. He gave a talk, colloquium. His wording is always say physics law can only be established by experiment and observations. Without the observation, all the model or theory are not totally true, or his words is wrong. Okay, so he encouraged physics students to try to do experimental physics, and then encourage all of us to do that. Okay, and he has a very strong opinion about how to design an experiment, the detector requirement. He always say we would like to build the detector always have a better at least 1% level if for mass detection or new particle detection. And so that is true. He built this kind of detector for the J particle discovery in 1974. I worked with him for many different kind of detector design and so on, which actually bring me into the atlas for the muon spectrometer work. Donald Glaser is the inventor of the bubble chamber. This is the poster again in front of my office, actually. And then he actually is the faculty during 1949 to 1959. Okay, he built this bubble chamber and can make the picture, as you can see here, to capture the charged particle move. Okay, in the magnetic field, of course, this charged particle, you can measure the momentum. His invention allowed the scientists to observe what happens to high energy physics beam energy research from the accelerator. So therefore paving the ways for many, many important discovery, the quarks, I mean the quark bound state, and also the, as I just mentioned, the neutral current. Professor Fred Bacchetti actually sent me a very interesting paper by him about the history about the bubble chamber discovery invention at the University of Michigan. Many faculty members actually in our department involved in this invention include Professor Byron Rowe, Martin Pearl, and so on. And Martin Pearl actually get the Nobel Prize by discovery of the tau particle in 1995. Okay, so this paper, I just read it, I found it very interesting. And I'm particularly interested in this to see the picture. You see the bubble chamber to take the cosmic ray muons, as you can see here. This is the trajectory of the cosmic ray muons detected in this kind of a bubble chamber by a very high speed camera. Okay, so that's amazing, the detector model. And then this chamber has been built in this 6 inches chamber, and then they had the beam test at the Brookhaven, and then you see the recorded tracks at the bottom here. This paper have a much more pictures interest, and I hope we can have a chance to look at it again. Okay, so we started the particle physics is the ambition to connect our elementary particle to the cosmos. So this picture show you the evolution of the universe from Big Bang at the very beginning, okay, 14 billion years ago, and the evolution to nowadays, this universe we live with, okay. In the early university, actually, the physics related to Big Bang evolution is particle physics. Because in early universe, you can see that is a lot of quarks and the gluons, electrons, and the neutrinos at a very high energy and at a very high temperature. And study this kind of early universe is not easy because it's already 14 billion years ago, and then you have to use the current measurement to derive what's happening. So particle physics have the way to do this kind of study, to have the accelerator. For example, we consider the Large Hadron Collider is in fact a Big Bang machine because it have the center of mass energy at 14 TeV and have the event rate at 1 gigahertz. Okay, with the LHC, we are exploring the force that governed in the universe when it was about 10 trillionths of a second old. So that means very, very early universe. Numerically gave you the feeling about the energy and also the time, temperature, and the distance. So that means we're probing the matter at the distance at 10 to the minus 18 meters. The idea about the accelerator is based on Einstein's very famous formula, energy equal to the mass times the c squared, c is speed of light. So energy can be converted into and create the new heavy on-C particles, okay? So therefore, that is our tool to study particle physics. So we build the LHC is for the new discoveries at the very high, at the TeV, trillion electron volts, this kind of energy scale. So I gave you a little bit of formula. I normally should not give a formula in this kind of talk, but here, I just say the proton beams will probe the matter you can consider is inversely proposed to the momentum. This is a famous formula. So if you use the calculation, you'll find out the proton beam, the wavelength actually is less than 10 to the minus 18 meters. Okay, show you in the picture, just like you use this kind of probe with very, very tiny wavelengths, you can go inside the proton to look at the structure. Okay, and then this is the we call the colliding beam experiments. We do the physics at this kind of a very, very small distance. So this is a cartoon to show the beauty of the E equal to mc squared. This actually is from a postdoctor from our group. Okay, so basically you show first of all two energetic protons have head-on collision, the crash together. Okay, and then this kind of collision can recreate the short life of the particles and uncover the forces and the symmetries that existed in the very early universe. And I draw a picture. This actually, the Higgs was drawn by me, a little bit of contribution for this cartoon. And actually, we indeed found out the new particles from the collision. So for this kind of physics, I would like to give you a little bit of feeling about how we need to take a picture. That means how you observe this kind of event. So I define each time protons collide, create particles in the final state, we call this is an event. We take a picture by our detector for each beam boundary collision time, that is 25 nanoseconds. This is a picture at the bottom, show you the event, Higgs event, detected in the 4 muon final state. Of course, this is not the photograph is reconstructed event. So at the LHC, there will be a billion of collisions event per second. Only one Higgs event can be produced from a trillions of collision event. You can see you have a tiny, tiny opportunity to see the event you like to detect. So therefore, we have to design a trigger system to only record the event where we feel is interest. But the experimental challenge is that there are big pile of events in a beam bunch collision in a 25 nanosecond. And this is at the round one, we have 25, as you can see here. There are many, many, many vertex. That means each vertex shows the collision, proton-proton collision. But you only from this many, many vertex here, you pick up the one you think that is the event you would like to study. This is round one, and round two, the vertex right now will reach 90. Every 25 nanoseconds, you capture a picture, it contains 90 events. You have to do analysis to pick up the one you're interested. So the ATOS experiment at the LHC is shown in this picture here. And just to tell you the scale, we put the graduate student as our ruler. That is our graduate student. This is a giant detector from the inner central tracker to the calorimetry measure the energy, and the outermost is the giant muon spectrometer, which we built at Michigan as a large portion. And this picture I show you is if I superimpose our detector into the LHC building at the CERN, that is LHC building, is taller than the 6 floors of the building. So you can get the feeling about the size. It is not only the size, but also you have to make sure it is very precisely measure the energy and the momentum for the leptons and the jets at the TeV energy scale for discoveries. Okay, this took our more than 10 years of the hard work for R&D and the construction. And we try to address the most fundamental questions to find out the origin of mass and also origin of dark matter. The mass is a very interesting question. We know mass from Newton's law, but from the fundamental particle point of view, the origin of mass is not so trivial. As you can see from this picture here, the vertical axis here show you many orders of magnitude different for all the elementary particles, different kind of elementary particles show up in the fermions regenerations, the boson, and also you see the W and Z is very heavy, about 100 GeV. However, photon is 0 mass. They are all the force carrier. Why they have so much different masses? And also the gauge invariant, as I mentioned before, require the mass of the gauge particle must be massless. So symmetry built in the theory must be broken. And it's the Higgs mechanism proposed by the Broad, England, Higgs. They are independent proposed in the 1960s. Elementary particle interact with the Higgs field to occur masses. In that sense, all the masses actually is the interaction energy with the Higgs field. So this idea actually can be seen from this picture here. So you can see this is the Higgs potential, okay? And overall, it has a symmetry in the theory. However, the ground state, that means the lowest energy state, okay, in this ring, the symmetry already broken, okay? The particle actually around this ground state of oscillation indicate that the Higgs boson exists. And this is called spontaneous symmetry breaking in our language. And then that leads to the particle generate masses, okay? So this is the, in picture, of course, theorists always write in the formula here, and this is Peter Higgs write down his theory in this Lagrangian here. And his theory actually is beautiful. However, he didn't tell us what is the mass of the Higgs boson. So therefore, when we search it, we do not know exactly where to search. It's a long story for us. And also he tells us, once you know the mass, you know how this particle will decay, because the decay depends on the particular branching fraction, depends on the mass as well. So for long time, at least since last century, 60s, it has been a very high priority in high energy experiment to find out the Higgs boson to confirm this mechanism is true. So to do this kind of physics, we need to have the additional innovation for discoveries. So Chabak at the CERN, so invented the wild chamber. And so then you can see that this wild chamber is smaller than his hand. Okay, at the very beginning, this was built at the CERN for discovery of the W and the Z, Rubia and also the Vandermeer get the Nobel Prize for this discovery. This kind of wild chamber actually is much more sensitive, particularly much more higher gain and also speed, allow us to do the camera basically much fast. And then so therefore, after the invention of the wild chamber, the bubble chamber is, I consider, just like a film camera become digital camera. Now that is our tool for discovery. And Chabak obtained the Nobel Prize for his invention of the wild chamber, which we continuously used in the modern particle physics. Myself actually heavily involved in the technology choice of the Atlas muon spectrometer, muon precision detector. I show you here that at that time we have 6 different kinds of considerations. And the 2 major ones. One is the wild chamber with drift cell cross-section. You have this kind of wild in the cell, this kind of configuration and anode wire in the center. Another choice is the Jupiter tube. You have the cross section. Is you have the cathode or tube wall, and you have a wire in the center. Basically, the electrical field in this kind of both cells are very similar, and also detector detection mechanism also very similar. You go through the avalanche of the particle annihilation near the wire, have a non-avalanche to collect the signal. And the wire chamber advantages have a very minimal multiple scattering, which will have the bad resolution for the tracks at no momentum. And then you have no tube wall here, okay? However, this kind of chamber, you cannot pressurize and the intrinsic resolution due to the electron diffusion is about 200 microns, okay? And if you have one wire broken, the whole chamber cannot work, okay? Then with some kind of R&D actually starting in 1989, together with Steve Allen and myself, will bring a proposal to Atlas for the pressurized Jupiter tubes as the muon detector. Why we would like to pressurize it? Because we would like to have the intrinsic resolution from 200 microns down to 80 microns per tube. More importantly, when we made the chamber, then if I have a wire broken, I'm only lost one tube, very small portion. So it's much more robust in the operation. So this proposal actually was accepted in 1995. So then we go into the precision muon spectrometer design and gave you some kind of idea why you have to build such kind of big chamber. This is because we require the chamber have to be very precise. This picture shows you the configuration of the chamber. We measure this dashed line here is the muon trajectory. Its momentum actually is proportional to the curvature, okay, of this kind of band, okay. R is the curvature here. And in fact, we measure the sagitta. And the sagitta is related to the size of your detector spectrometer, air, and inversely proportional to the curvature here. So therefore, we have to design a detector. We say, okay, magnetic field probably around 1 Tesla. And then in order to have the very high resolution at the TeV muons, we'll have to build the detector air around 10 meters, more than 14 meters in the end cap. So therefore, for the muon resolution, you just propagate from this relation, which is proportional to the uncertainty of the sagitta measurement here, okay? So you have to measure your detector with this kind of configuration. You have to measure the sagitta with the accuracy less than 50 micrometer. This actually is smaller than the size of my hair with this kind of 40 meters large detector. So that is our design goal. For 1%, if the muon PT is 100 GeV and 10% PT is 1 TeV. So the layout of the muon spectrometer is based on this kind of design idea. I spent my sabbatical year at the CERN in 1997. From that, I met with Homonier, and then I came to Michigan to build the largest precision muon detector. I get extremely strong support from the physics department. And almost all the big buildings like High Bay, Chalk Bay, and all the student shop gave to me to build this detector. And you'll notice this, the lab at High Bay, when we build this infrastructure, we'll have to break the wall in order to move this granite table, move in. And then we have to build the underneath of the earth and of the floor to another bigger support. Otherwise, this very heavy, strong flat surface will not be put into our lab. Okay, right now we still use it for the upgrade detector. Okay, this is at the high bay. And then I have to mention that in addition to the detector construction, we have to build ultra-fast electronics. I have to tell you that is the Jay Chapman is the project leader for this. His architecture is shown in this product here, and the real detector, the electronics was designed and built at the Michigan. And that allow us to take the picture as this very, very complicated detector display at the LHC. And Jay won the US Atlas Lifetime Achievement Award last year. So this is the first time we have a very large team at the university to build such kind of a large detector. This is the picture. When we finish the chamber construction at the Michigan, when we started the chamber, build the large wheel at the CERN. And when we finish this kind of project, and the National Science Foundation actually sent us a very warm congratulations letter to the US muon team, okay, because such kind of experiment or the detector hasn't ever been built in the university, always in the national lab. So then we build this very large spectrum muon detector at the CERN. This is the sector, and then we construct it in the pit. This is the wheel, and you can see that is the Michigan physicists install the cables, okay? And then you can see the people at the bottom of this one. So that tell you the scale of the detector. So this detector is not only big and also precision. The most important I would like to emphasize is the coverage at the ETA 2.7 never build, none of the particle physics experiment build the coverage like this kind of small angle, which allow us to accept the Higgs event at 70%. Without this detector, the Higgs acceptance in the barrel only have something like 35%. So once we build it, we turned on in 2009 and 2010. In a few weeks, we observed this all the resonance, this Nobel Prize, Z, J psi, and so on, all of that by the momentum, angular, and the energy measurement. And the momentum scale and the detector resolutions right match as we designed. And our detector efficiency is 99.8%, close to 100%. So we consider the first year we should observe the supersymmetry, but we didn't. But we really discovered many this kind of new particles. That is our standard candle. So we hold the first year LHC conference at the Michigan, and that at that time we have the group for Michigan group had this photo in that conference, celebrate the LHC turn on, and we are all the detector we build work beautifully. Now, of course, our purpose is to discovery. In 2011, only at the 7 TV, we first of all to see a hint of the 4 muon event. And in fact, we observed the 3 event. And the prediction is only 0.3 for lepton background. So we were very anxious to know if this event is really the Higgs or is just the other production, electroweak production. So we waited until 2012. LHC actually increased energy from 7 to 8 TeV, increased the event rate. Then we had the 4 lepton event observed. Then is clustered, as you can see, in the 125 GeV. Okay, that actually gave us so exciting observe it. When I reported this in our department, the seminar, one professor asked me, you have to be very careful. This may not be the discovery. This could be the fluctuation. True. Then we continue rediscover this particle. Now nobody will say this is not a fluctuation. This indeed is a particle. So in July 4th, this Higgs signal was observed at the LHC. Fabiola, our ATA spokesperson, gave a report about the discovery in 3 different channels. Would like to mention that Professor Chen of Michigan group is the team leader for discovery of the Higgs to WW. And our another experiment at the LHC CMS also see the same thing and the same location of the bump observed. So therefore, we have no doubt this is a new particle observed. So therefore, this is just a picture. The DG of the CERN say, we got it. When he says so, and immediately everybody said, oh, we see it. Okay, Peter Higgs and England also was invited in this special seminar. So is this discovered Higgs is indeed the Higgs boson? So with very limited statistical, we already be able to do the hypothesis test. And we confirm that the observation with 2 different kind of hypotheses. This is the spin 0 particle as predicted by the Higgs mechanism. Many tests was done with different kind of hypotheses. As you can see that all our data is in favor of spin 0 and the parity positive particle. So this is a confirmation of the new particle discovered is Higgs. So therefore, Nobel Prize is awarded to England and Higgs. And for the theoretical discovery of the mechanism that contributed to our understanding of the origin of mass of the subatomic particles, and which recently was confirmed through the discovery of the predicted fundamental particle by ATLAS and the experiment at the CERN's Large Hadron Collider. And we continuously measure the mass because this was not predicted by the theory. So, and gave you the history of the mass measurement by the ATLAS experiment. I would like to very happy to say that our mass resolution from the measurement is much better than 1%, is only 0.2%, much better than some teams' expectations. And I also would like to tell you that the 4 leptons, the mass measurement gave you the lowest uncertainty here, which is dominated by the 4 muon event by ATLAS measurement. That is the detector we built. Okay. Then we further discovered the Higgs decay to the fermions and established a new law of the nature. As you can see, many order of magnitude different in the couplings, which is totally different from the gauge coupling, which is universal. Here is non-universal, and each particle have different kind of couplings with Higgs. That is the origin of the mass. Okay. Then I would like to mention that the Higgs to mu is a very challenging measurement, and was recently we also found out the hint. This have 2 PhD theses, okay, from Michigan here. So we also use the Higgs to probing the dark matter. The idea is that since dark matter is about 85%, okay, something we do not know what is the component, but it only have the observation with through the gravitational effect. Since Higgs coupled to the mass, okay, so therefore we take it as a portal between the particle and also dark matter particle. So the search at the CERN actually is invisible. So Higgs can decay to the dark matter particles, okay, and then we look at the signal by the tag either from the Z or from the forward backward jets. And then from here is the new result from ATLAS. If you have a dark matter particle coupled to the Higgs boson here, you would like to observe the red line here. But the data show that it consistently only with the background hypothesis. Okay. So therefore, we have not yet be able to really tell the dark matter coupled to Higgs. where current limit is the Higgs, the branching fraction Higgs be able to decay to the dark matter is less than 11% at the 95% confidence level. Okay, so Higgs is a new strategy used as a tool to probe many new physics. So ahead of us is a big challenge to probe many advanced physics topics listed in here, the big bubbles, okay, which actually designed for the roadmap of LHC will continue the research. And just to mention to you right now, we are only at 5% of the data set LHC is designed to deliver. So therefore, I think we are still in early stage for further new discoveries. We are very busy to upgrade the detector for these discoveries. Now, finally, I just mentioned that the super collider at the CERN is already under the plan of the European strategy. As you can see that the LHC to me is very big, 27 kilometers. And the CERN will build another next generation collider at 100 kilometers near Geneva here to study particle physics in the next several decades. So finally, I would like to thank for the very strong support from Michigan Physics Department and the LSA, and also thanks to the US DOE and the NSF strong support to support our large team at the Michigan. And this is the photo as you can just capture in the 2015. At the same time, we take the picture for people at Michigan at the CERN. And lastly, I would like to say that we are in deep memory of Professor Homer Neer and Rudy Tong. They are both foundation faculty members for the Atlas Michigan team and made this discovery possible and made this. So Rudy passed away in 2022, right after Higgs discovery, and Homer passed away 2 years ago. Thanks. Any questions? I see some kind of questions come out of here. So first, the comment is from the Fred, who sent me the history of the bubble chamber development. He said actually, the development of a bubble chamber is at Michigan, not at Berkeley, as introduced by our dean. Okay, so I think that I already gave you the reference of the history and documented by Fred. Hopefully, everybody understands that. Another question is from I have considered the data, and I have thus determined that gravitons are tiny particles. First of all, graviton has not been discovered. Okay, so we are not sure is the idea, a particular gauge theory, is the right theory for gravitation and predict the graviton. The major reason is the gauge theory is based on the internal symmetry, and gravity, the symmetry particularly is the waves is the space-time, okay, the whole gravitational wave. So therefore, I have to say graviton is not necessarily the right symmetry. We have not even see it, okay, and the graviton may squeeze a neutrino between the magnetic field. Maybe Owner, you can tell your idea if you would like to comment on this, because your comment is very long.
So can you now hear me?
Yes.
Oh, Professor Zhou, I'm so sorry. We had a Zoom issue and I could not unmute myself. So I'm sitting here hopelessly. So thank you for going into the Q&A on your own. And again, so first let me say thank you for this really wonderful talk. I'm so sorry that you are having to do the questions on your own. So so let me grab a couple more of these. So we've got, since 1930, we have no proof of dark matter. How about the supersymmetry? Any prospects of finding proof of that at the LHC?
So you say 1930, okay. In 1930, the invention is for the accelerator, and we do not have the supersymmetry idea yet, probably because supersymmetry idea, I believe, is developed much later, around the 70s, 60s. Okay. However, the invention of the accelerator is try to look at the particle. In order to look at the particle, you have to crash it, and then you have the detector look at it, so that you can understand the internal structure of the particle. So therefore, it is the acceleration of the particle and the crash. Then finally, we discover the quarks inside the protons and the neutrons. So supersymmetry by itself, actually, in when we starting the LHC, actually everybody said in the first year you will discover the supersymmetry. Unfortunately, we didn't see it. You know, supersymmetry is a beautiful theory model, but unfortunately, actually myself, the PhD thesis was looking for supersymmetry. Actually, I have to say, it's not only LHC we're looking for supersymmetry, but so far this idea, we're still looking. We are not yet give up, but at least it's not so easy as originally we thought.
So we'll hit one more question, and it looks like maybe my camera is not working at the moment. And I'm hoping that this question makes sense to you. Where is the artwork commemorating U of M's contribution to the LHC?
What is the artwork? What kind of artwork?
I don't know. So that question that may not make sense to you either. So, and I want to thank Fred Bichetti for the correction on where the bubble chamber work was done. So Professor Zhou, I know we are here at 5 o'clock. I am just, so we're going to have to wrap this up, but I want to thank you for this talk. And I have to say the images you shared were just beautiful at so many points. It was really such a pleasure to get to see, and to see what these technologies look like for those of us who are less familiar with them. And if you could see me, which I think you cannot at the moment, and I hear from our tech person that we may be having some broadcast issues with Zoom at the moment, but I have a framed poster for you of your talk, which is one of the ways we like to commemorate this talk for you. And so we will get this to you so that it can be something that you remember this talk by as well. But congratulations. Thank you so much for sharing this talk with all of us. And thank you to everyone, we had almost 150 people here. So thank you to all of you who were here for the talk. And again, Professor Zhou, congratulations.
Thank you very much.